All right, a couple more concepts that are really important to understand to have a good foundation with our gases. Here we see some important plots representing some number of molecules or probability of molecules being at a certain kinetic energy or speed. Because remember, we oftentimes work with temperature and gases, and our temperature, of course, is a measure of kinetic energy. And now, what these plots are showing are what is known as the Maxwell-Boltzmann distribution curves. Now, with gases, more so than liquids and solids, we can have a wide range of kinetic energies of particles. Okay? So, when you first look at, let's say, this picture on the right, if I didn't have T equals 150 Kelvin and T equals 350 Kelvin, most people, when they see this, say, oh, this must be the higher temperature because the curve is higher. Oh, it sticks up higher. But that's not true. All right. When our gases are at a lower temperature, the particles are slowed down and more of them have the same kinetic energy. So at a lower temperature, you will see a much narrower and taller peak because that means most of the particles are at that speed, that kinetic energy, that temperature. Whereas when we start to heat a gas up, you will see a much wider distribution of the kinetic energies. And so you'll have a flatter curve, and you will see that, yes, there's still a majority of particles here, but you have much more to the left and to the right of that majority. I know my art skills are amazing. But you can see that a little more with the plot on the right. Okay, as the temperature increases, so the probability of molecules having higher energy increases. So at 0, a much higher hump, so most of the particles are at that amount of energy. Then 25 it flattens out, and 100 flattens out even more. And we're going to see these curves later on too, especially when we talked about like activation energy and reaction mechanisms. But right now it's important for us to know that with these gases there's a wide range of kinetic energies, especially at higher temperatures. And so we might see a problem looking something like this. On the left I have a drawing. There I have a diatomic gas, and the arrows are representing the direction and amount of speed that these particles are moving. And I'm saying that this container is at room temperature. Let's call it around 300 Kelvin. So now I see two containers on the right. Same gas, same number of particles, just I want to know which of the containers, A or B, represents the gas at a higher temperature and which one at a lower temperature. Now hopefully you picked A to be the higher temp and B to be the lower temp. And again, because we're looking at the average kinetic energy. So yes, even though letter A, I've got this little guy who must have just came off a collision or something and has a very low amount of kinetic energy, the other arrows are way longer. And so the average kinetic energy in that container will be higher than what we saw at room temperature. Whereas down here in B, all the arrows tend to be short, and if we average them together, it would definitely be lower than what we saw at room temperature. Okay, so that's again a visual concept of a question that could potentially show up somewhere along the way. All right, whether it be in my own test or an AP exam type question. All right, a little introduction to gas stoichiometry. Again, we'll do more later because, well, as it says here, anytime we're using a mole ratio from a balanced equation, that's what stoichiometry is. So anytime you're solving a problem and you need a balanced equation and you're looking at one substance in the equation compared to another substance, that's stoichiometry. So yes, we can do gas stoichiometry because maybe we could say, we have a solid that emits a gas and we want to know how much of the solid will produce this amount of gas. So that's a stoichiometry problem. Or maybe how many moles of gas produce, anything like that. Now we will see later on, oftentimes they might make us solve an equation, perhaps like the ideal gas law. That's pretty popular. That we'll have to solve the ideal gas law, perhaps for volume or moles or something, and then use that piece of information in a stoichiometry problem. We'll be doing that when we do our hovering bubbles lab this unit. But a big concept I wanted us to see are these go to completion problems. On the AP exam, gases are quite often tested, and a lot of times there might be a whole bunch of information and maybe 3 or 4 multiple choice questions coming from that, or it's part of an extended response question. And so within those, there's always some simple questions that sometimes get muddled and very much confused because it's like, oh my gosh, I had no idea how to do that. So I just want to make sure we kind of understand this whole go to completion concept. So here we see I've got phosphorus pentachloride. It decomposes into phosphorus trichloride and chlorine gas, and they gave us the all-important balanced chemical equation. All right. And so it says a pure sample of PCl5 is placed in a rigid evacuated 1 liter container. A lot of information in that statement. Okay, again, this is probably part of a longer group of multiple choice questions. Okay, first off, they gave us a 1 liter container. That's very nice of them, especially since we can't use our calculator on the multiple choice parts. It's an evacuated container, meaning there's nothing else in there. We put the pure PCl5 in the container. There's no nitrogen or oxygen or anything else. And then we see the rigid container. That means fixed volume. Our volume won't change. It's not a balloon. It won't expand and contract. It's a rigid container, so it'll stay 1 liter. Now it says the initial pressure in the container is 2 atmospheres. All right, and we see this is our figure 1 initial container, 2 atmospheres. The temperature is held constant until the PCl5 reaches equilibrium with its decomposition products, and we see that in the figures below as well. Now, are we equilibrium experts yet? No. Do we know what equilibrium is? Perhaps. Okay, we've got this reversible reaction that we see up here, and equilibrium is a reaction kind of gets stuck. It's not done. It's just when the forward and reverse reactions are happening at the same rate. So it's kind of stuck in that position. And so it gives us information about that equilibrium. So yes, I'm sure there will be equilibrium questions as part of this information, but for right now I just want to focus on this question. It says, if the decomposition reaction went to completion, what would the pressure in the container be? Now, pause and think about it, but this really goes back to a fundamental thing that we said earlier on, is that gas particle collisions cause pressure. More particles, more collisions, more pressure. And so the reason why I have this here with the stoichiometry is I have to look at my lovely balanced equation. I see that 1 mole of this PCl5 gas decomposes into 2 moles of gas. So if this reaction went to completion, if it didn't get stuck at equilibrium, 1 mole of gas would turn into 2 moles of gas. And since my initial pressure was 2 atmospheres, the pressure now would be 4 atmospheres. That's it. Twice as many moles of gas are in the container now if it went all the way to completion. So that's twice as many particles, twice as many collisions, twice as much pressure. Get it? A lot of people are like, oh, I had no idea what to do. It's just that simple part. Don't forget the easy peasy parts, please. Last question. Okay, here I have a before the reaction and after reaction vessel. I see that the red circles are nitrogen, the open circles are oxygen. So before the reaction, looks like I have some O2 molecules and I have some NO, nitrogen monoxide. And after the reaction, it looks like it's making nitrogen dioxide, NO2. So what's the balanced equation? Well, I've got some NOs and O2s making NO2s, but how many's? So when I do, I see a particle problem, I typically need to count the particles. So I see that I have 4 O2 molecules and 8 NOs. So I have twice as many NOs as I do O2. And then over here, I have 8 NO2s. So I have the same number of NOs and NO2s. And so you could, count up all the things. You could say I've got 4 O2s and 8 NOs make 8 NO2s, and then I would just reduce that down. So ultimately, 2 nitrogen monoxides plus oxygen make nitrogen dioxide. Again, I could have said 8 NOs plus 4 O2s make 8 NO2s, but I'd want to reduce it down. So here's the question now, though. Does the pressure in the container increase or decrease as the reaction goes to completion? And why? So hopefully you've paused and thought about it, but again, particles, collisions, pressure. Before the reaction, I have 12 particles in here. I have 3 moles of gas. After the reaction's complete, after it's gone to completion, I only have 8 particles, or 2 moles of gas. So either way, I hope you said it's going to decrease, because the products have less moles, or less particles, but somehow you got to relate that to saying there's less particles at the end of the reaction than there were at the beginning, therefore we'll have less pressure. Alright, I hope this helps, and I'll see you soon.